we were talking earlier, okay, we're going to be doing energy states of atoms, energy states of atoms. And remember what we were talking about before is that atoms, when you excite them, emit energy, or you have absorption, where it absorbs very specific energies. And what actually happened was that these spectral lines, especially from the emission spectra, are very specific. And what people noticed is, remember what we were saying before, E equals HF? What they noticed is that if you took the energy from the one of the emission line, you could find that it would often equal two other frequencies. And two other frequencies, when added to gives you a third. So we might have a frequency of one light, and it would have a certain amount of energy. So we often draw it like that. So this is the amount of energy this way. So this is going to be one photon. But two of the other lines, if we take the energy from two of the other lines, hold on, they add together to that. And what this showed us was that light basically existed, well, basically the energy being emitted from an atom, which is excited, is in very specific levels and bands. And then a guy called Niels Bohr, remember I was saying he was actually he was a postdoc student of Ernest Rutherford's for a year, believe it or not. And he's the one that came up with the Copenhagen interpretation of quantum mechanics as we know it nowadays, which lots of people swear and curse at. But he basically said that the electrons in a hydrogen atom could only exist in very specific energy states. So it was always assumed the electrons could be in any frequency, but he was saying no, it can only be in this frequency or this frequency or this frequency, because the frequency is related to energy. Therefore, it can only have this amount of energy or this amount of energy or this amount of energy, and therefore the energy of the atom could be quantized. And he came up with this formula: the energy at any specific point is equal to negative 13.6 electron volts over some factor which we're going to call the level squared. But this value n is going to be is integer value 1, 2, 3, 4, very specific. And what this told us basically was that if you looked at an electron, so let's look at a hydrogen atom, because hydrogen atoms are simple. You can do this with other atoms, but way beyond first year physics. You can have an electron, and we always think of electrons being in orbitals going around. We know that's not quite true now, but it could be in this is the ground state. This is the smallest, closest that the electron can get, and it can't get any closer to the electron. The reason why this isn't going to be inside the neutron is due to quantum effects, which is okay. But this electron can be what we now call a shell or a level, but it can also, if we put in energy, it can be in a separate level. Or if we put in more energy, it can be in a separate shell. So basically what we could describe was, we figured out that electrons exist in these shells or these layers, and this represents how much energy. So if we stick in energy into here, the electron will bounce up a level. When it drops down a level, then, so if it goes down, it will emit a photon. It will squirt it out. And the amount that it can go up or down, so you put energy in, the electron goes up. The electron drops down, it releases energy. And these are going to be, due to quantum mechanics, which is Niels Bohr's speciality, these are very specific levels. And you might ask, what's this negative 13.6 electron volts about? The answer is very simple. If you put in more than 13.6 electron volts, you knock the electron off the atom altogether. So basically 13.6 electron volts is the most thick atom. So basically what happens is, how much energy does it take to go from there to there, or from there to there, or from there to there? And what we'll actually often draw this is this is the ground state. This is the level 1. This is the lowest energy that the lowest state the electron can be, and this is going to be the closest to the proton. And then we're going to draw another level in here. It's going to be level 2. And because you'll notice that this equation had level squared, as these go up, these get closer together, and so on until they hit infinity. And so the amount of energy to transition from one level to the other, the change in energy, is going to equal the level you're going from minus the level you're going to. Well, the energy is going to be the energy from the level you're going from to the energy you're going to. So it's going to equal negative 13.6 electron volts. And then we go 1 over n squared minus 1 over m squared. Basically, that's just rearranging this equation, but we'll put the two together. We're basically taking that equation and then simplifying it down, believe it or not, and that's going to be measured in electron volts. And so this energy, this frequency, is going to be emitted. It's going to have the change in energy of h. And these, remember, these levels are quantized very specifically. So we actually give these names series. So if an electron is jumping all the way down to the bottom level, doesn't matter. It might go from, from the 4th level down to the 1st level, the 2nd level down to the, we call this the Lyman series, after the physicist that first proposed this. But we also have a series here. We can have an electron jumps from the 3rd level to the 2nd level, the 4th level to the 3rd level, and so on. These are going to be called the Balmer series. Balmer. And so on. So basically every one of these series has got a name describing them. So if you go from 4th to 3rd, or 5th to 3rd, or 6th to 3rd, there's going to be the Paschen series. And if an electron jumps from here to here, it gives off visible light. Isn't that cool? Because these represent 13.6 electron volts, negative 3.4, let's put these in. So this is negative 3.4 electron volts. So if an electron jumps from here to here, it's going to give off 13.6 minus 3.4, it's going to give off about 10 electron volts. 10 electron volts, the frequency is beyond visible light. And the further it jumps, the more electron volts it's going to give off. However, if it jumps from, say, here, negative 1.51, down to here, it's actually going to be in the visible light range. And this is actually, so what can actually happen, there's a couple of things that happen. If you look at fluorescent light bulbs, for example, what they have is they have a vapor tube. So in a fluorescent light bulb we have a vapor tube with lots of atoms in there, usually mercury or something. And what you do is you excite those up a couple of levels. You excite them up a level or so. So now the electrons get really excited, and then they drop down a level and they give off ultraviolet light. Poof. And then these hit a material where this is actually a slightly different shape. Remember, this is only for the hydrogen atom. So if the material in here is designed so that it gets absorbed here and drops down, poof, and gives off visible light. So we've got two substances. We've got emission in this frequency, and then, because basically we electrically charge it up, the electron gets excited, then it drops here, and it heats up there. Okay, so anyway, what's happening at this point is, okay, so basically how much energy is required here. So let's actually do an actual example. So what we have, find the energy and frequency. This is example 8.4. Find E and F of photons emitted for hydrogen, for H atoms transitioning from level 2 to level 1. Okay, so the change in energy is going to equal energy level number 2 minus energy level number 1, which basically we've already worked this out, so it's going to equal negative 13.6 electron volts times, we're going from 2 to 1, so we're going from 2 squared to dropping to 1 squared, which is equal to, let's work this out, 1 divided by 2 squared is equal to 1 divided by 4, minus 1 equals 1 divided by 4, 1 divided by 4 minus 1, I divided by 1 there, equals negative 0.5 times negative 13.6 equals a change of 10.2 electron volts. Don't worry if you get these around the wrong way, just out of interest. All that's going to happen is the sign is going to be wrong. But in this case, it drops from there, so we're emitting 10.2 electron volts, so it's going to be positive. What frequency is this going to equal? Frequency, well, we got up here, is going to equal change in energy over H, which is going to equal 10.2 electron volts over, remember this is going to be in electron volts, a Planck's constant 4.136 times 10 to the negative 15 electron volt seconds, which is equal to 10.2 divided by 4.136 x minus 15 equals 2.466 times 10 to the 15 hertz. And what that means is it's emitting it as visible, as ultraviolet light. Remember, visible light's usually in the 10 to the 14 hertz range. This is 10 to the 15, so it's higher frequency. That's going to be ultraviolet light. And so, it's pretty cool. So basically, the big thing you have to remember, the big takeaway you have to remember from this one is light is quantized. Well, the energy levels that an electron can have is quantized in, so it can be at level 1, level 2, or level 3, level 4. So it's very specific, these energy levels that they can be, dropping down from energy levels from 2 to 1, or dropping down to energy level 1 will give you ultraviolet light, dropping down to energy level 2 will give you visible light, and dropping down to level 3. So basically what happens, as I said with this fluoro tube, you put an ultraviolet light, This absorbs ultraviolet light, pumps up, drops down to level 2, gives off visible light, and then your fluoro tube works. Yay!